In this segment, I want to continue our discussion of waves, and I want to introduce probably the most important of all of the wave equations. So in the previous chapter, we talked about simple harmonic motion. And we talked about simple harmonic motion simply because it's described very well with sines and cosines. And so it's a type of motion that we can deal with mathematically in a fairly straightforward fashion. And it gives us a jumping off place to study more complicated types of repetitive motion if we wanted to, including waves. So if the source of a wave is simple harmonic motion, then the shape of the resulting wave will also be a sinusoid. Well, what exactly does that mean? Here is a device that can produce a wave. And how does it produce a wave? One of these strings vibrates back and forth. When this string vibrates back and forth, that's well described by simple harmonic motion. This string vibrating back and forth is simple harmonic motion. The equilibrium position is right here. If I displace it from equilibrium and let it go, then it vibrates back and forth. Since this motion of the string is simple harmonic motion, it produces a sound wave that is described well by sine waves, just as the motion of any point on this string would be described well by sine waves because it's simple harmonic motion. The good news is that this is the only type of wave motion we'll study in this class. We need a little bit of terminology. The wavelength is the distance from one successive peak or trough to the next. And the period is the amount of time required for two successive peaks or troughs to pass through a given point. And of course, those units are seconds because it's a time. So the period here is not really different from the period that we learned about in the previous chapter. It's still a time for one complete cycle. Yet, because we're talking about a wave, these things are flowing past us, right? If we're talking about a sound wave, right, that means that there are areas of compression that are hitting my eardrum, right, one after the other. The period then would be the amount of time between successive points of compression or of high pressure. And again, these are moving through the air, right? So I can just stand in one place and wait. Oh, there's a compression. Ooh, there's the next compression. How long did it take between those two? That is the period. Similarly, the wavelength is, if we could just freeze time and say, okay, how far is it from a point of compression to the next point of compression? That is the wavelength. Graphically, it looks like this. If we're graphing here displacement versus x, so this is a snapshot here of this wave, right? So notice we've got position and not time here, right? And so maybe it's almost like a picture, right? Maybe this is a water wave or something like that. Maybe it's a wave on a string. The wavelength is the distance in meters from one peak to the next. Now, be careful. Notice this wavelength is the same if I measured from trough to trough, or peak to peak, or crossing going up to the next crossing going up. So it's from any one point to the next corresponding point. And if I was standing over here and watching this wave come towards me, then the period would be the time interval between one of these crests hitting me and the next crest hitting me. Recall from chapter 14 that the amplitude is given by the distance from equilibrium. How far from equilibrium, right? So it's half of the total height of the wave. Okay, I call this the big money wave equation. Velocity equals lambda times f. This is a relationship between velocity, wavelength, and frequency for sinusoidal waves. It's a fairly straightforward equation, but there's actually a lot of physics in here. One of the most important points that we need to remember when we're using this equation is that the wave speed velocity, generally speaking, is determined only by the type of wave and the medium that that wave is traveling through. So, for example, a sound wave, the speed of sound is 343 meters per second, approximately. And that's the speed of sound for all frequencies and all wavelengths. So something like this that has a very high frequency and a short wavelength travels at the same speed as a sound wave like this, which has a longer wavelength and a lower frequency. Both of those notes, those pitches, right, the high pitch and the low pitch, they have different frequencies, they have different wavelengths, but they have the same velocity. Why? Because they're both sound waves moving through air. Similarly, light waves all travel at 3 times 10 to the 8 meters per second. Right here we see some yellow light that's traveling through air to the camera on my computer. And here's some blue light that is traveling from my shirt to the camera through the air. Well, what's different about those two? Well, yellow light versus blue light, they have different wavelengths and different frequencies. Since the blue light has a shorter wavelength, it has a higher frequency. The yellow light has a longer wavelength and a lower frequency, but they both travel at the same speed. Why? Because they are both light waves traveling through this room. Okay, so the speed of the wave is determined by what kind of a wave traveling through what medium, and not by the specific frequency or wavelength of the wave. That gives us this relationship here. Notice we can graph this in terms of the, again, as defined in the previous slide, the period is the amount of time between successive crests. Let's do a quick example. For this sinusoidal wave, what is the amplitude? Pause the video. I'll see you on the other side. Hopefully, you said 1 meter. It's 1 meter because the amplitude is the distance from equilibrium position to a peak. Notice it's also the distance from the equilibrium position to one of the troughs. What is the wavelength of this wave? Hopefully you said 2 meters. It's 2 meters because we need to look at the distance from one peak to the next. That's 2 meters. But notice that it's also the different distance from one trough to the next trough. It's also the distance from one crossing going up to the next crossing going up. Notice that if we just go to the next subsequent crossing, that's only half of a wavelength, because this is not a corresponding point here, right? Here we're crossing and going up, here we're crossing and going down. We need to go to the next one, that is also 2 meters. What's the frequency of this wave? Well, for this one, we need to use that equation that I just gave you, the big money wave equation. V equals lambda f. That means that the frequency equals velocity over the wavelength. In this case, I've given you the velocity on the chart there, 200 meters per second, divided by the wavelength, which we previously described as 2 meters. Therefore, my frequency is 100. Standard units in, we better get standard units out. Hertz. Not too bad. So, the speed of sound varies with the medium. Sound travels, about 343 meters per second. That's about 750 miles per hour through air. Again, it varies slightly with temperature. Light and other electromagnetic waves in vacuum and air move at the same speed, 3 times 10 to the 8th meters per second. However, sound travels faster through water and even faster still through a solid. So we need to be a little bit careful with that. Typically, we're going to deal with sound waves in air. Now, light and other electromagnetic waves, so they travel in vacuum and in air at the same speed, 3 times 10 to the 8th meters per second. So light is just one example of electromagnetic radiation, but there is a broad range of phenomena that are all electromagnetic radiation. All the way from AM radio waves, which have wavelengths on the order of a kilometer, so a half a mile or something like that. FM radio waves are about the size of you or I. Microwaves tend to be centimeters long. You know what? Your cell phone communicates by electromagnetic radiation, right? We might think, oh, I talk on it, so it's sending out sound waves. But no, right? Your phone converts sound waves that you produce into an electronic something or other in here, which is then broadcast and communicated with a cell tower as an electromagnetic wave. The wavelengths that your cell phone uses are something like this. We'll do an example about that in just a second. The microwaves that cook your food, that's electromagnetic radiation. In that case, we're talking about wavelengths something like this. Moving on, we've got infrared, even shorter wavelengths, but too long for you to see. We don't call this light because our eyeballs cannot see it. You and I are actually sources of infrared light. Because you and I are not at absolute zero, we are giving off light in the infrared region of the spectrum. Now there's this narrow slice right here in the middle, between about 400 nanometers and about 700 nanometers, that we call visible light. We call it visible light because humans have eyeballs that are sensitive to these frequencies. Moving on to shorter wavelengths. Here we have ultraviolet light. This is so-called UV radiation. This is what gives you a sunburn. If you sit out in the sun too long, our eyes cannot see it. And of course, X-rays. X-rays have such a short wavelength and such high energy that they can penetrate the soft tissues of our body, but they get stopped by our bones. As we go to the right on this graph, we have higher energy and shorter wavelengths. As we go to the left on this little chart, we have longer wavelengths and lower energy. All of them are examples of electromagnetic waves. So all of them are wiggling electric and magnetic fields, and they all travel at the same speed, 3 times 10 to the 8th meters per second. Here's a quick example. Cell phones use radio waves to send signals to cell towers. A typical frequency used by Verizon is 700 megahertz. What is the wavelength of these radio waves? So the FCC actually controls access to the radio frequency spectrum. And so a company like Verizon actually has to bid on and pay money to the US government in order to use chunks of the electromagnetic spectrum for their business. And so Verizon happens to own a chunk right around 700 megahertz. How long are these wavelengths? Well, let's just see. We're going to use this equation again. In this case, we're looking for wavelength. So solving this for wavelength, we get V over F. Well, what is V? In this case, we're talking about radio waves, which are electromagnetic waves, which travel at the speed of light. Divided by the frequency, that's given in the problem. We want to convert that to standard units so that we are assured we'll get standard units out. Now all we need to do is run our calculator. Okay, I ran my calculator and I got 0.43 meters or 43 centimeters. All right, so 43 centimeters is something like that. Right? There you go. Here's another quick question. A speaker emits a tone of a particular frequency. Suppose the air temperature increases. What happens to the wavelength of the sound? Why don't you pause the video? I'll see you on the other side. We're going to need a couple of equations to make it through this problem. First of all, this is the equation for the velocity of a sound wave in air. Notice that as the temperature increases, the velocity of sound also increases. So the speed of sound in air is going to stay the same. So the speed of sound in air is going to increase. If the velocity increases, well, this speaker is still wiggling at the same frequency. So the frequency will stay the same. The wavelength must increase to compensate. If the velocity goes up and the frequency stays the same, the wavelength must increase. It turns out that large stadiums, indoor stadiums, will use this idea right here to control the temperature of their stadium, right? In your house, you probably have a thermostat. I have one. It's upstairs, kind of by the kitchen. You know what? For a fairly small house, that works pretty well. Because, the temperature at one point in the house is probably pretty close to the temperature in the rest of the house. And if you have a well-designed HVAC system, it's going to work out just fine. But if you're talking about an enormous stadium, like, I don't know, the Pepsi Center that can hold something like 30,000 people, well, knowing what the temperature is, over by the men's restroom is just not that useful of a way to control the temperature in the entire thing. And so what they'll actually do is they'll actually send sound waves across the stadium at a frequency that humans can't hear, so it doesn't bother anybody. And the stadium is big enough that they can time how long it takes to make it across the stadium. By timing how long it takes to make it across the stadium, they know what the speed of sound is in their stadium. And therefore, they have a nice idea of what the average temperature in the stadium is. And so this is the basics behind how you might design a thermostat system that would be measuring the average temperature of some enormous, enormous room.